Thank you, Karen. My name is Lee Blackwell, and I'm a solutions architect here at Databricks. I recently joined after a pretty lengthy career all in the big data space, and I'm just so excited to bring my data engineering knowledge and background to Databricks and really do some awesome things here. I candidly haven't done a lot of image processing in my data engineering life, so it's so exciting to see what Databricks can enable for us to do with these images. So excited to bring this episode to you guys. How about you, Franco?
That's awesome. Thanks, Lee. Hey, everyone. My name is Franco Patano. I'm a solutions architect here with Databricks. My background is data warehousing and BI. So I've spent a lot of time managing data, and now I help customers figure out what this Lakehouse thing is on Databricks. So with that, Jason, you want to tell us a little bit about yourself and what you do?
Sure, Franco. Yeah, I'm Jason Roby. So I'm a solutions architect here at Databricks as well. I currently run the enterprise platform subject matter expert group at Databricks to help customers with challenging problems, and was real excited to run across this one with image processing that Rohit and I will be able to share with you today.
Awesome. And hi all, I'm Rohit. I'm also a solutions architect at Databricks. My expertise has been in data science and data engineering and helping our customers build applications on these. And like I said earlier, I'm based out of Seattle and looking forward to interacting with you all.
All right, thanks everyone. So today's episode is about images with Delta Lake on Lakehouse. Well, wait a second. I thought Delta Lake was for structured transactional data. What did you guys do here?
Yeah, so this one was an exciting one. I'm gonna pull up my screen right away. So yeah, it's kind of the normal run-of-the-mill schema process, and do some text analytics and some quantifying. Now, with this customer, what this use case did is we wanted to look at images. So we were pulling the customer we were working with was pulling lots of information from a manufacturing process. And ultimately, they wanted to bring in the power of deep learning using some GPUs to detect certain conditions. So we basically came in and helped them with generating of images. In this case, what we'll go through today, I'll show this, but we kind of shortcut that and just pull some images for classification. And then inference and send out notifications. And then we also had a data science model. What was kind of interesting about this use case is, aside from the fact that we're dealing with image data, instead of kind of what we normally think of as database data, is the cost of running and maintaining GPU instances basically was such that the team had to run a cluster of like 4 or 5 fixed machines, very large GPUs, and we're really struggling with thinking about how to scale that out to all of the company. And so what we wanted to do is come in with Spark and Delta Lake and Databricks and show how one, we could take kind of what they were doing from they're using pandas and some traditional single core type stuff, and really not have them change too much, yet come in and let's do some data processing now, and let's give you a scalable solution out to the rest of the system.
So Jason, real quick, just to really understand this from a super high level,
Yeah.
What can this help, and I'm sure we can't really talk exactly about the customer, but
Sure.
What does this help the business do, and what were they not able to do before this?
Sure. So for this particular use case, we are getting after really quality control on the production line. And so going from kind of manual spot checking type, and not really, I'm oversimplifying and protecting some details probably, but really from going from a kind of a statistical sample set into almost like a full out with using this deep learning model and using the periodic adjustments in the model with a seamless production inference chain that we'll show you, able to get to like 100% automated checks with which have some degree of control and check with the manual process that was also being run. So it was pretty effective idea for them, and it was the concept was in an R&D stage, and so they were really excited about it, but then they really needed to figure out how to scale it out.
Yeah, I think that's a good point. I mean, we're kind of only in our infancy of being able to do such image processing, right? I mean, we're the big data world is really tabular and more traditional business reporting. So I mean, it might be still sort of a niche, point for image processing. I'm curious if anyone out there live is actually working with image data or has a use case. Chime in. We're interested to see what's out there. But
Yeah, what's also interesting to me about this specific instance here is kind of some of the decision points that were being made. So this was when we're talking about like they had to have all of these GPU-based machines. These were capital investments for on-premises architecture, correct? So like can you talk a little bit about how painful that is for this instance, just doing what you're trying to do? And then when you went to the cloud, right, we're taking this and we're helping with migrating these workloads to the cloud. What were some benefits that were you able to obtain, like infrastructure wise? Can you touch on that a little bit and how like that process went?
Sure. Yeah. So yeah, the customer was using a very large Hadoop-based cluster to do things, and with the deep learning and kind of the abilities to just unreasonable effectiveness of data type learnings, really wanted to pull in GPUs where we could really crunch fast. And so to R&D it out, they literally had to go buy a small cluster, put it in one of the facilities, and really develop out their system. It was impractical, let's say, to distribute that across the existing infrastructure based on licensing and all this other stuff. So they literally had just these large boxes, which they self-managed, self-clustered, and then developed out the model. And so one of the first things that was a concern is like, yeah, sure, you guys can come and help us, and you're doing this other stuff over here working with text data, but I'm doing images. I've had to customize this. It's going to be too expensive. Well, no, what we were able to show is now I can pull in and really use GPUs on demand and then get rid of them. You don't have a capital investment. If you come back to it in 6 months, you get new GPUs, which might have the latest model. And really focus on using that here, keeping a nice streaming, just regular class machines, as it turned out, running your day-to-day production. So it really gave the customer the ability to use the power where they need it and pay for it only when they need it, and then really give them a economical stream through. And then plus, since we're in multiple regions and it's easy to deploy and manage Databricks across multiple regions with multiple workspaces and such. Now we can just take this solution and effectively copy and paste it. So, reality, probably CI/CD and code check-in and all that stuff, but really just move it out so that we are effectively bringing compute to the data where the data is. But yeah, that showed a lot of value. And what was neat for this is with that custom hardware solution, what we got in this was a big improvement, and just being able to use the binary column types in Delta Lake, which I'll walk through here shortly, and run this on streaming system with clusters available on demand and such. We were still able to get a 45x improvement from what the customer was already doing, and really.
Sorry, 45x?
45x, yeah.
Ooh.
Yeah, so, well, there's actually two numbers. One of them wasn't measured very well. So there's a 3600x for just image generation itself, but that I think has to be examined more closely. But 45x for this stream right here. So coming from source measures, I've got little disks here from to represent data sources, but starting with that source and then getting all the way into inference, we did 45x the amount. And when I did as much as I could, kind of a core and GPU comparison. Actually, we didn't use GPUs on this, but kind of a core and RAM comparison about equivalent hardware with what they were doing in bare metal and having to do extra work to kind of manage the distribution and such.
So another thing I kind of want to articulate out here is that when you're talking about a manufacturing process, let's talk about the business for a second, right?
Yeah.
So from a business perspective, like the whole Six Sigma industry is around this, about the manufacturing process, about improving your processing capabilities and reducing the amount of failures or things that go wrong, right? And so when we're talking about from a business perspective, like how a manufacturer who makes widgets, right, for example, if they could lower the amount of waste, they can increase their margin. So we're talking about not only is the technology itself more accessible and
Right.
more cost efficient, but now I want to touch on something you mentioned before, sampling with the data science versus now we can do it on the entire set.
Yeah.
What does that really mean? Like explain like the business impact of checking every single widget in the line.
Yeah. So it's super easy. Anyone working with data is going to know that as you kind of subset data down and try to figure out what the best way, whether you use stratification or just random sampling or some other technique, you're likely to miss things. And we all know from statistics that you can build a sample set and say various things fairly quantifiably about the whole set. But when you're dealing in something where you have to produce and that becomes your business, and even percentages of increase over something that you produce 1 million of can mean a significant amount of extra product. This was very appealing from the business side to be able to get back into kind of a full check with even a percentage-based model that wasn't human. Obviously, we're not replicating humans, but we're getting at their smarts here. So two aspects really helped here. The yield. From the end of the day, there was a kind of a long process, let's say the manufacturing process, and this is early on. So from this, the idea was, well, help identify these things up early so you know ahead of time before getting down in later stages, which might be months down the road, that either you've got a bad batch, you've got a poorly functioning tool, something like that, or you have corrective steps that you can take now to make that yield in 2 months much better. So from kind of a time efficiency perspective, we were helping them with that. The other side is, as a developer, as a data scientist, it's sometimes difficult to iterate quickly. And because of the way I was working in notebooks, and Rohit and I were working in notebooks, because of the way that Databricks is already set up to kind of subset things for you, you can really move along and iterate in seconds, and then give this what was taking 30 minutes, but now it's taking 2 minutes to run through all the data set. You can get that full data set while still being able to iterate on a small sample. So then you get time efficiency to really explore ideas within even a production cycle, giving you the ability to adjust something now instead of in 2 weeks, and giving you the ability to get yield in 2 months and know that you can guarantee that, versus waiting and having to throw away a whole batch of product.
Notebooks, you say?
Yes.
Is that what we're looking at right here? Shall we dive in?
Yeah, let's do it. Sorry. So yeah, we literally use notebooks for this, and let me go through some of this. So I'm going to go through some of the actual code, some tricks that we ran along the way to kind of make this good. So as I tried to mention earlier, customer already had some Python code. They were already doing some image processing and didn't really want to go and redo all their models and all their processing work just to try a new platform. And great thing with Databricks is I can pull in what we need. So I'm pulling in some standard libraries here. And then I say the actual code, this is obviously not what we're doing, but we wrote a generate image function. So for this use case, we're not starting with source images again. So I'm just pulling them together. And in this case, I'm doing something simple. So I'm just writing a dot when you pass in a set of input rows around this object that we took a picture of. Really, the deal there is I want to show how to kind of integrate the single core and take advantage, single core kind of mode of development, and take advantage of the parallelism offered by Spark. So then getting into the actual here, what we had were basically two tables to pull together. One had kind of summary view and one had some real detail. So basically in Spark now, I'm just pulling in from a couple tables, putting them together, and then getting it set up so that I can do, and I do a little math here, but getting this set up so that I can do the actual image generation. What was kind of interesting about this is using, I just lost my mouse. Here, let me plug that in. Sorry about that.
You write very clean code, Jason.
After a few edits, it becomes clean. So I do try to make this, we try to make this into something that is understandable once we hand off our POC. Okay, so yeah, back to, so right now, this is where I'm going to start using the function. So in this case, I'm going to use this somewhat new apply in pandas function that requires a grouped data set. So I'm going to do this by the interest ID. And then it also requires a schema. So one of the first things I had to wrestle with is, do I hard code a schema, all this kind of stuff that you sometimes run into. And, just a quick aha, hey, Spark is lazy. Why don't I just pretend like I'm doing a select just to get the columns and types right, and drop that down. So that's what we did here. I just set this. This doesn't actually create any data operations. It just does a one-time schema lookup from the job perspective, provides that return. And then as long as I have my distribution okay according to my cluster, I can just call that generate image. And this by itself, this is that the super fast image generation, because I'm able to distribute out chunks of my incoming image information, and then distribute that across the cores. So that turned out to be pretty easy.
Wait a second. Hold the phone.
Yeah.
Hold on before you go on, because the next step is awesome. But I just want to articulate something here, because you covered it. But it's you have a lot of information, right? You obviously spent a lot of time on this. What Jason just did was he took that regular Python code, not PySpark. He took regular Python function and he put it into a function called apply in pandas, which under the covers will distribute that according to the clause and group by. So in this instance, it's taking interest ID, right? And it's using that as the key to distribute and using regular Python code. This isn't PySpark. I don't, that's a huge call out, because I get asked all the time, like, I know Python, am I gonna have to learn PySpark? And it's like, not really. There's so many other options with Databricks. You don't have to. I just wanna call that out here. Do you have any stories around that?
Yeah, so I've used this a couple times. It's really, every time I start with somebody, you've already basically started solving the problem using pandas, using standard image libraries, this kind of thing. Kind of similar, not as often on Scala, because if you've gone to Scala, oftentimes you're dealing with Spark directly. But this proves to be, this is one way to get pandas functionality. You can also directly use our Koala's open source project, which is pretty neat. Given functional compatibilities, I really wanted to stay close to what the customer was already doing, and really help. Just let's use the power of Spark for what it's good for, and put a nice wrapper around this guy. And so with that, there's one more thing I should call out that was a gotcha here. Maybe a tangent from the question, but the other thing I needed to do here was really filter out the data, because when you use the apply in pandas to do your regular stuff, Spark is literally going to take all the data that you specify and send it over. So what I wanted to do is subset that, and I have a, here we go. Okay. Interest with image should be what this is. There we go. What I needed to do is subset that off into just pulling off the columns that we need. Otherwise, all of that data, every single row would be sent here. And so, and then the other thing that's kind of nuanced about using this is you want your return data frame to match the schema that you set. So I had to do the same thing here that I did up here. to take this now as a pandas data frame, and Spark, because of the magic of this function, Spark is going to automatically convert that. When the data comes back, it'll immediately go from the pandas chunks, which are suitable for a single core, into the distributed data set that comes here. And this is probably wrong, but I'll fix it for when we publish this and make this available.
No, it's totally cool. In the interest of time, I know we've got a lot to cover with the ML stuff. So let's go through this. This is also another big point here. How you're using Delta Lake. And this is, I think, the reason why I'm super interested in this. Let's talk about this next step.
Cool. So yeah, well, I'll cover this kind of briefly here. It's the magic's in, let's take advantage of the fact that we have a binary column type. And then just put your images there. So what we had with this customer case is we had a bunch of potentially small files. So these were generating small images. You can do this with larger images, and I haven't personally proven out the edge yet. But what's nice about it is you let Delta Lake manage putting even several images in the same file, avoiding ripping through your block size and such. So the other thing that was important here is, since I'm dealing with PNG data in my image generator, I've already got it compressed, and the rest of the data, and even if in this case, I had about 35 different columns to put in next to the image, which, by the way, makes it super convenient to work with the data with the image right there without having to do some weird join or file lookup kind of a thing. But anyway, so when I had all that data together, you're not, compared to the image data that's in here, I'm not going to get a lot of benefit with compressing the other rows. So I just turned compression off. And in this case, I'm grabbing what it was set to. Then I run through and just say, well, let's just tell Delta to do its normal thing, which by default is snappy, and just go to uncompressed, write it out, and then restore where we were. And as a final follow-up on that, I actually put this is how I like to do data jobs. I want to write to disk and know where it is, and then treat the metadata as kind of a follow-on label shortcut. And so that's what we're doing here.
So Jason, one question just to clarify, because you said a lot in that, which was amazing. But the way you used to see it is that you would you'd store the pointer to an image in your file store somewhere in your data set, and that's how you'd grab the image. But you're saying that we're storing the actual image data right here within the Delta table.
Yeah, because I've brought that image data back with my apply in pandas.
Okay.
The first thing I'm going to do is I'm going to join that back with because I subsetted that column wise so that I wouldn't have a lot of serialization work going between the pandas and the Spark. But then brought that back together, put everything together, and then with that image now, it's just a binary column. I'm not using the Spark image. That's useful for other things. I'm using a binary column. And now it's just columnar data. It's going to be put efficiently in the right spot. And now I just write out the table like any other kind of data. It doesn't look any different.
Awesome.
Sweet. And then a final bit that is cool about this. So downstream, now I'm going to be able to, in this case, I'm actually showing you that image type. So this isn't what comes out of the binary. This is some of the loading that Rohit is going to go through. But at the end of the day, when I want to use this guy, here it is. What we were able to do is in this case, we're using Keras and TensorFlow, and Rohit will talk about that shortly. But what I wanted to do is give the data scientists the flexibility to bring in whatever platform and bring in whatever insights they wanted to ultimately be able to take and do the classification that they needed in production. So you want to be able to do that without this huge coordinated effort across lots of organizations within your company. So in this case, we extended, Rohit can talk about this a bit, but we extended the MLflow PyFunk flavor and grabbed the pipeline code that does any kind of specific tensor transformation into it, so that When we pull this out, this code would never have to change. So as we're running we do some of the same tricks that we were doing before using the applying pandas, this kind of stuff. But now I can just pull out a PyFunc model from MLflow and whatever it is, including its pipeline, transformation into TensorFlow or into PyTorch or whatever's needed to get that data set can be included as a part of the model and registered with our registry. So that final step, like we talked about image generation, and now this is the inference side. Now I can run that in production all day long and then have that data science truly as an out-of-band process. As soon as it publishes, the next run of this guy will get the production version, and I don't even have to care if it's PyTorch or Classic Spark or whatever. So I think next thing we should probably go and look at the data science element with Rohit, but I guess any questions on that stuff?
That's a great segue. Yeah, that's definitely. So Rohit, while we're switching screens to you, I just want to ask you a question. How valuable is it as a data scientist to have an engineer as brilliant as Jason Roby?
It is super critical. I mean, otherwise I'd be spending about 80% of my time, either dealing with setting up, GPUs and such complicated stuff, and two, much more importantly, having somebody like Jason, figure out, hey, Delta is pretty cool to store images. So if I'm coming in and building a data science pipeline, that makes my life a whole lot easier. So kind of taking that one step further, we've seen some examples from some of the other work we've done. Taking a sample here, now we'll go through a few notebooks, kind of the bottom of the box that Jason was walking us through. This is the training pipeline, right? Like, you can have the training done in Databricks with distributed computing. And then you can have a stream that's running, 24/7, where it's actually inferring and, applying the model that you've trained onto live data. And technically, if your use case demands for something that's, ultra low latency, you can even deploy it on an edge device, right? You can take a model that we've trained here and then deploy it elsewhere too. So there are a lot of options depending on what you want to do. Here in this ingest step, what we're going to look at is kind of similar to what Jason showed us in 0.0 ingest, but we are going to use a slightly different data set and see how Delta, handles image data. So kind of jumping right into it. You see here, I'm trying to list and see, hey, what is the folder structure I have of this flower photos? You can see that there are a few folders underneath. I'm just going to see, hey, what's underneath that? So I'm just picking Daisy, for example. There are a lot of JPEG images down here. So now the tough question is, okay, this is all great, but it's unstructured data. How do I put a structure to it? Well, it's pretty simple. In Databricks, you can just say, hey, spark.read.format image, and just point to that particular folder. What you see here, which is pretty cool, and I really enjoyed seeing this the first time I used it, was you see the image thumbnails and the labels automatically picked up. That's it. It's literally as simple as that.
I'll stop being surprised by seeing this. Like, I just love being able to display images right there.
Right. It helps you with QC. It helps you understand what you're looking at, rather than looking at something that's a little too complicated. And for those of you, we know there are a lot of data scientists and data engineers here. You can definitely look at the more interesting stuff under the hood when you unselect this preview, and you can then see it has a pointer to where this image is, what its metadata are, and the number of channels. In this case, it's color, so 3, and so on. So it's very useful to kind of to be able to do that. Let's say you have, now this is a case of, kind of inferring the target variable label automatically through the folder structure. Let's say you just have a bunch of JPEG images in a folder. You can simply, again, use the same format of, read.format and pick it all up. So that's pretty nice. As you can see here, I have, a whole bunch of sunflowers. Now that, we are able to see how Databricks and Spark lets you, pull in data as a structured table, let's kind of make that a little more concrete. What we're going to do is we'll read it in and we will store that data. So I'm just going to reuse the same stuff, spark.read.format, and point to that particular location. We've seen this just before, but this time around, I'm going to save it. I'm going to save it as a Delta table. What that lets you do is then you can have, just like a structured table, but actually having unstructured image data under the hood. In this case, you can see here, I have this particular database. I'm just going to take a look at this table I've created right here as a delta table. And you'd see that it actually captures all the schema and the sample data that is just popping up. So that makes it really easy for users to come in and check all the data about how big it is and things like that. Another cool thing that Delta lets you do, you can actually have time travel. So even though it's image data, as you keep modifying, as you keep adding to it, you can actually go back in time and say, hey, give me this table as of a particular timestamp, which is super useful for a data scientist when you're trying to reproduce an experiment. Otherwise, you have to tell your boss, well, I had one data set, I tried something, I got some results, but I can't reproduce it anymore. So no more of that. Now that we've seen quickly as to how you can store the image data assets in Delta format, what you would also experience often is you want to save like terabytes, like tens or hundreds of terabytes of data, image data in a table, in which case we actually recommend saving it as a binary format, which doesn't give you the cool thumbnails here, but it actually makes it much more efficient to store and to be able to process it, especially to process the data as you put it through the paces in a data science pipeline. So all you need to do is just say binary file and make sure it's picking up all the JPEGs, and there you go. And with that, there's some basic stuff I'm doing here, like extracting the label. All of this, by the way, is Python code. In fact, 90% of the code that I have as a data scientist is all in Python, like probably 90 to 95, just barely 5% that is in PySpark. So it makes it really easy for data scientists like me who is comfortable in Python to move into this world. So here I'm just doing some basic transformations, and I have all these metadata stored in, and I'm going to transform the label to an index and just finally again materialize it in Delta format. So I have a Delta, and I'm going to write it again as a table. Like Jason mentioned, you want to use uncompressed rather than snappy. It makes it extremely fast to use. And that's this table that we have right here. Let me jump to that if Zoom lets me do it. Okay, Zoom is not helping. But anyway, there we go. So that's the table we're talking about. You can see the binary image stored here. Now that we are able to get to that, let's take a look at how we can then take this and use it in a data science pipeline, because that's the real use. What we'll show you is how you can load the data in Spark. You can then use this particular library called Petastorm that allows you to load terabytes of data into any of the deep learning frameworks, like either TensorFlow or PyTorch. You can use that to then convert a Spark data frame into a format that TensorFlow or PyTorch understands. You can first do a single node training like you would do in your laptop or on a simple server. And then we'll show you how you can do it in a distributed fashion across a cluster of GPUs. So note that here, the particular cluster that we are using actually has the GPU instances that under the hood, which makes it extremely fast and powerful, especially for training libraries. You can see here it's got the 2 NVIDIA GPUs. So that's the kind of stuff we're using for training aspect. I'm just going to switch over. Pausing there for a second. Any questions?
Yeah, I got a question from LinkedIn from Miguel. Can we reconfigure parameters in deep learning algorithms approach used for trained model? So I know that we're covering this in a couple minutes here, but if you want to touch on that for a second before we get there, or if you want to talk about that right now, feel free.
Yeah, I think I'll just cover it since it comes through in the flow here. But yeah, you can you can do things like distributed hyperparameter tuning, and you can pass it on in terms of distributing the parameters that you use in a particular model. Now, again, the exact parameters, that really depends on your use case. What we're going to do here is a transfer learning. So you can take a pre-trained model, you rip out the last layer of it, and then you just retrain it. In fact, this example works for 100 images. So, many people think about deep learning as requiring terabytes of data. That's not true. You can do it with very small data as well. But kind of jumping right in, what we do here is we set an MLflow experiment that will allow you to track the progress of each of the experiments that you do. So, you're building many things, you lose track of it. That doesn't help. So what this lets you do is it'll keep a track of what notebook you're using, which version of it, what data source you're using, and what are the parameters and metrics of the models that you build. Makes it so much more easier for you to, as a data scientist, to understand what is going on. We have some simple parameters like image shape. Sorry, was there a question there? Okay. Image shape, 224 by 3. 3 is the number of color channels. And then we load back the data that we had in the ETL pipeline. You can see here, we're just doing a simple split for training and validation. You want to repartition it to the number of workers we have. So in this particular cluster, we have 2 worker nodes. And that's why I have that repartition set to 2. And the other cool thing here, this is something we learned as we did the project. So Petastorm is great to help you do that sort of a transformation from a Delta table into a TensorFlow dataset. But we ran into some issue where we were not able to understand why the amount of data that was being read in was too high. And then we realized as you convert a regular Delta table into a Petastorm format, the Parquet row group size, which is the amount of data that Petastorm caches, it does this cache. That's the library that we set here. You want to keep that to a relatively lower value for massive data sets, because otherwise it can be like the default of 32 megabytes can be too high, and you might run into issues. So that's a pro tip that we learned during our project. But once you convert this using Petastorm Spark Converter, you can then directly feed it into your libraries, which means you can actually just switch out TensorFlow that we have here with PyTorch, and everything just works.
Wait, what?
Yep. So there are a couple of things that we really focused on in this pipeline, which is anything a data scientist does is restricted to the notebooks that he or she is working on. Anything that corresponds to the inference pipeline that Jason was handling should be completely insulated, which means the ETL shouldn't change just because I'm switching to PyTorch, and the inference shouldn't change because I'm switching to PyTorch or some other fancy new library that comes across. And Petastorm is one way I can ensure that the input remains the same no matter what library I use. Literally, it's one line that I need to change if I had to use PyTorch. And I'll show you in just a sec how that works in MLflow on the inference pipeline, where you literally have to change nothing. So yeah, you heard that right. So jumping right in, you can see here we have about 3,000 images. I'm not going to go too deep into the model because really it's just any TensorFlow or PyTorch model that you want to use. Some of these examples we used from TensorFlow's samples. You see all of this, by the way, is Python. I'm just creating a simple model using my transfer learning mobile VNet model. That's trained on ImageNet weights. So it's kind of pre-trained. You don't really need a whole lot of data to retrain this. I compile it. I can see the summary of the model. And all of that is Keras in TensorFlow. Then once you have a model that's ready to be trained, you want to pre-process the data. So you can see here, this is again a nice piece of info. Because our information is stored as binary, you want to actually use a bytes.io object to then convert that and then feed that into image.open. What they'll let you do is then do any transformations you want to do, like resizing or rescaling. So for example, pre-process input is something that TensorFlow's mobile VNet to library provides, where it'll actually rescale things down to an image that is ranging from 0 to 255 is brought down to -1 to 1. So again, very nice transformations. And Petastorm also allows you to do some transformations on the fly, so you don't need to do everything beforehand. And that's why you see I'm using, again, simple Python, pure Python functions to do my transformations. Once I have that, I'm going to jump right into using Petastorm to kind of feed batches of data. So you don't have to feed 10 terabytes and then spin up a supercomputer. You can do it on a relatively small cluster. And all these are, again, TensorFlow code, you just fitting the model. And this is another super cool thing that we were able to do, which is how you ensure that the inference pipeline doesn't change whether you use TensorFlow or PyTorch. All you need to do is create a class that extends pyfunc.python model, implement a predict, which does all the transformations of data that you feed in through an inference pipeline. So in the inference, instead of a binary, I'm going to feed in a regular image. And this takes care of transforming that into something TensorFlow understands and predicts on it. So you can see here, it's actually applying the model. So the data scientist can then deploy a PyTorch model. They just need to make sure that the predict function here is modified to deal with how PyTorch does it. And the inference pipeline doesn't change one bit, not one single character in there. So that's another very cool way of making sure that you save that model. And
That's awesome.
What you would see here,
extensibility at its finest.
exactly. And what you see here, I'm just going to quickly jump through since I know we're getting close to time, is I'll show you the model that we built. You can store it and save it in MLflow model registry. And I'm going to click on the latest version, which I marked as production. So as data scientists develop new models, the inference pipeline doesn't change because it's just saying, hey, pick the production version of the model and give me that, and it'll just apply it. So somebody can come in and say, I have a V4, I want to promote that to production. Again, the inference pipeline doesn't change. So that's another critical piece. You can see here, it actually tracks the run that corresponds to the one that created that model. And when I come down here, this is the generic pyfunc flavor. It'll tell you how you can use it. You can load it as a Spark UDF or as a pandas function. So then you can really use it anywhere. It's not saying that you have to use it in Spark alone. That makes it really powerful to use.
And you can see here, right? I could see here what notebook reproduced that run from this view, right?
You can, and that's a good point. You can see here all the metrics. You can see here all the parameters. You can see exactly which version of the notebook that created it. And you can actually go ahead and click reproduce run, which will use the same cluster and the same notebook and reproduce the exact run. So if your boss asks you, hey, what was that? You can actually prove that to him. So
I have one of those like mind blown emojis right now going.
Definitely a powerful toolkit. It's been fantastic to work with.
And here, we just to close it out here, we have a simple run on a single node. So think of it like running it on your laptop, but on a much more powerful laptop. You can see it worked quite well. Validation accuracy of 0.9. You can then simply convert it into something that works on a distributed cluster, a cluster of GPUs using Horoward Runner. So that's something Uber and Databricks kind of developed and worked together. It's again an open source library. You just need to make sure you invoke callbacks that allow a distributed training of the model. And the rest of it is practically the same thing as what I had earlier. Just make sure we point the callbacks. And that's it. Again, do note that all of this is Python code. You can see here that I start the run. I just say Horoward Runner, initiated. I have two nodes, two worker nodes, each having 2 GPUs. And I just need to hit run against that particular Python function that I've defined here. And boom, I have multiple GPUs. As you can see here, it'll say GPU 0, GPU 1. All of those are being used to do a distributed training of this particular worker. So that's an awesome example of how you can use most of the Python functions that you're familiar with and ensure that your inference pipeline is really solid and you can try out anything you want and ensure that it goes through a governance process of model deployment. With that, I'm going to pause. Not sure if we have much time for questions, but happy to take any.
Thank you. That was excellent. All right, we don't have any more questions. The questions that were asked, I think we've answered them. There is one thing I think that if we have time to answer, we might want to. But there was a question from Aman saying that what about if you have larger images, like satellite images, for example, where they're gigabytes or terabytes or petabytes in size? My initial response is I thought that chunking was a very common practice with that, like satellite data in particular, because you can't process, the curvature of the Earth and all that, because you can't really put it like that. Jason or Rohit, do you have any experience with that, or do you have any thoughts about how you would do something like that really quick?
Yeah, no, I've worked with geospatial data a bit, and I usually break that down into tiles, or it's already broken down into tiles, and then each of those tiles conveniently fit in. I've got some other use cases that we're developing. We need to push the limits of how large of a file you can get. By default, um, outside of images, so delta breakpoint for or the delta write size is around 2 gig. And so anything up to that, definitely we're going to get quite a bit of benefit out of using this. As you get into these larger files, I have noticed that a lot of them are actually just a join together of several files that can break up and file, and I can turn it into a table. So there's some future work to do, but I do want to see. I haven't taken this to the breaking point. I know I can get up to 2 gig and still get pretty much all of the benefit that we've covered today.
Yeah. And just to add to that, I haven't actually implemented using Petastorm with geospatial data, but Petastorm exactly helps you do that, in that you can load batches of Parquet data. So as long as you have it stored in a Parquet file, literally terabytes worth of it, Petastorm can load it in batches so that your server is able to handle that without running out of memory or anything like that.
Yeah, that mapping into the GPU is the critical bit, and so Rohit showing that with Petastorm. We'll make sure. I mean, the future work on this, we're still in the lab here, so future work is to really push the extremes and see where we can go and keep the code this simple, basically.
All right, with that, we had one more question come in. If it's a quick answer, I know that Karen's got to get ready to outro us, but if it's quick, Anthony is asking, what do you mean by scaling image to -1,1?
Sorry, I don't know where
Sounds
that
like
was. Yeah, I'm not sure if we haven't done anything of that nature here. So I'm not too sure about that.
It is a common practice to generate extra images. If you have a smaller image set and you want to make sure a class is represented appropriately through rotations, people will do things like that. I don't remember that specific transform, but also built into several of these ML toolkits, you'll get that kind of rotation because it's an ideal scenario not to have orientation of the image actually affect the object detection or what the classification. I don't know if that's what you're asking about, but that scale of -1,1, if it's in here somewhere, would be a flip, and it's usually not required for these deep learning algorithms because they'll automatically rotate if you parameterize it. So
awesome. With that, thank you, Jason and Rohit, for joining us today. Really appreciate you collaborating with us.
My pleasure. Thanks for having us.
Thank you.
Yeah, thanks so much. I'm just gonna also thank you, Jason and Rohit, and thank you, Franco and Lee, for hosting this session of Data Collab Lab and for joining us on the online meetup group. So, and thank you everyone for joining us. We have another session coming up in a few weeks, so I'll make sure I pass along all those details. If you're joining us in Zoom, you'll get a message through the meetup group when that's announced. And if you're joining us on LinkedIn and YouTube, again, I encourage you to join the meetup group so you can check out what's coming up next. So this video, it was live and it'll be recorded. It was recorded and it'll be available on YouTube shortly after. So with that, I'm going to just do a quick thanks for everyone again, and we hope you join us next time. Take care.
Thank you guys. Have a good one.
Bye.
Thank you, everybody.